Section 2.3 Conditional Probability and Independence. In this video we are going to look into the definition of statistical independence. Two events, A and B, are independent if the probability of each event remains the same whether or not the other occurs. If the probability of A is different from 0 and the probability of B is different from 0, then A and B are independent events if the probability of A given B is equal to the probability of A. So that means there is no condition on B. And also the probability of B given A is equal to the probability of B. So for the conditional probability, A doesn't really matter. If either the probability of A is equal to 0 or the probability of B are equal to 0, then they are independent. Now, let's have a look to mutually exclusive events. So, by definition, the probability of A given B is equal to the probability of the intersection divided by the probability of B. And by definition of independent, this should be equal to the probability of A. If we swap B and A, so we have the probability of B given A is equal to the probability of the intersection divided by the probability of A. And as it is independent, so that should be equal to the probability of B. So notice that we have the two events A and B, and the intersection is different from 0. Now for mutually exclusive, the events are going to be, the intersection of the events is going to be equal to 0. So the probability of B given A is equal, by definition, of the probability of the intersection divided the probability of A, and that's equal to 0. But the probability of B is different from 0. So therefore, events A and B are dependent. And that actually makes sense. So consider two events, like you flip a coin, you have head or tail. They are not intersecting, event head or event tail. They do not intersect. But when you have head, you know that you are not getting tail. So it's depending one of the other. By being exclusive, you are able to determine some information of the probability of the other event. So you need the events to intersect to be mutually independent. Let's look into an example. In the case of the manufacture of the rods again, we already compute the probability of the length being okay given that the diameter is okay. So that was this intersection. And so let's have a look to some conditional probability here. So let's have a look to again the same problem. So we have E1 is the probability of the diameter being okay, and E2 is the probability of the length being okay. So what is the probability of E1 given E2? So that's equal to the probability of the intersection divided the probability of E2. And we already solved it, and that was 0.9 divided the probability of E2, 0.942, and that's equal to 0.95. If they are independent, this probability should be equal to the probability of E1, and the probability of E1 is equal to 0.928, and that's different from 0.95. Therefore, E1 and E2 are not independent. On the other hand, if we look two different events, A and B, A being the event in which the length is too thick, and B the probability that the diameter is thin. So, and the question is, what is the probability of A given B? So that's the probability of the intersection divided the probability of B, and the probability of the intersection is 0.002 divided by the probability of B, which is 0.5, and that's equal to 0.04. And if they are independent, this probability is equal to the probability of A. So what is the probability of A? Is 0.040, and these two numbers are the same, therefore event A and event B are independent. Now there is an interesting rule, and it's the multiplication rule, and we have been using it before. So we have two events A and B with the probability of A and B being different from 0. Now, by definition of conditional probability, we have these two expressions, and what I'm going to solve is for the intersection. So in this case, we have the intersection of the probability of the intersection of A with B, and in the second case of B with A. By solving, so we have this multiplied by the probability of B is equal to the probability of the intersection, and we can solve in the same way for the second case. So we multiply the probability of A by the probability of B given A. Okay. Now, if they A and B are independent, we also have the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. So if we combine this with these two, we have that the intersection, the probability of the intersection is equal to the probability of A given B, but we can replace it by the probability of A, and we keep the probability of B the same. And in the second case, the probability of B intersected A is equal to the probability of B given A, which is equal to the probability of B multiplied by the probability of A. So what we have is that the probability of the intersection is equal to the multiplication of the probabilities of each one of the events, if the events are independent. Let's have a look to this example. So we have an airplane with a redundant system to measure the angle of attack. So we have event A, which is the main sensor fail, and event B, which is the backup sensor fail. And we have the probabilities of those events. And we are going to assume that they are independent. They should, because we don't want that one system depend on the other, because that's supposed to be redundancy in an airplane. And we need to find what is the probability of both fail, and we really want to have that probability low. So by definition of the probability of the intersection of the two events A and B, so the main fail and the backup fail, is going to be equal to the multiplication of the probabilities of A and B. So we have 0.05 multiplied by 0.1, and that's 0.005. So that's 0.5%. So that's apparently low. We can organize this information of events that are independent in a tree. So let's have a look to a tree. So we have the main sensor and we have the backup sensor. So the main sensor has two possible outcomes, either fail or work, and the backup system also have the two different outcomes, fail and work, and this is for the case when the main work, the backup will fail and work. So we have the probabilities for each case, and because they are independent, at each point they should add equal to 1. So that's why we only knew the probability that fail, but the probability that work is going to be 1 minus 0.05, so that's going to be 0.95. The same way for the backup sensor, so we have the probability that fail is 0.1, but we know that we have only two options and the sum of the probability should be equal to 1, so the probability that work is 90%. So to get the probability of the intersection, so in this case the intersection are going to be the branches, so fail and fail, and in the contingency table is going to be given by that, and it's 0.005. The probability of both work, that's going to be in that branch, and that will be 0.95 multiplied by 0.9, and both work is equal to 0.855. And then we have the probability that the main fail and the backup work, we also want to be that one big. Apparently is not that big. Fail and work, 0.045 fail and work, and the probability, finally the probability of work and fail, that's 0.95. and that is how we also organize this information in the contingency table. Thank you.